Okay. So yeah, I have the pleasure of welcoming Sebastian back to Berkeley. I had the pleasure of being in the same office of Sebastian for about 1 week before COVID started. But nonetheless, it was a very fruitful collaboration. Sebastian, I would say, is one of the leading experts on probabilistic verification. And so having him here today, there's a lot of questions about verification in AI, and I'm sure Sebastian has a lot to say with all 1 million environments.
Thanks, Marcel, for the kind words. Thanks, Sanjit, and the organizers for having me. And thanks to my co-authors, because this is, of course, not just my work. So when I had to think about, okay, I'm going to give a talk, but what am I doing in the trustworthy AI space? And I had to think really hard. Then I thought maybe I can tell you a little bit about probabilistic verification challenges that have overlap with the trustworthy AI problems, or in particular with this guaranteed safety AI program. So just in order to get you all on board, but with this crowd, I think this is going to be easy. We're looking at, this is basically Sanjit's paper, for Sanjit's picture from yesterday, right? We have a system, and for us, that's an agent or a policy. And we have a world model and the environment, and that it's going to be a Markov decision process. And we have some specification, and you can think about expected reward or reachability or LTL or whatever kind of specification you really want to think about today. It doesn't matter that much for this talk. And then there's this policy evaluation question, which I would call Markov chain model checking question, where we want to know whether the system and the environment together satisfy the specification, and if so, by how much. And then there's this policy synthesis question, or MDP model checking. And here we're not actually inserting the agent as part of the input, but we're only giving an environment and a specification, and we want to know whether it's possible to find a policy such that the specification holds, and if so, we also would like to get that policy. Yeah, and in this talk, I will motivate some of these challenges, and then the spoiler is that those will be generalizability or robustness and compositionality. And in the end, I will talk a little bit about monitors as well, because I like them. I thought they're important in this context. So I will start with shielding in reinforcement learning, and Bettina will give a extensive talk about this. So I'll only use this to motivate a little bit of what kind of problems we're thinking about and why I think they might be useful. So we have this reinforcement loop. The agent has some goal, and they are trying to learn how to achieve this goal. But from the outside, we only want to allow actions which are productive and safe, so they don't violate some rule. The agent is never going to drive off a cliff. And also somehow I want to make sure that the actions that I'm allowing, that they will ultimately contribute to this goal of maybe reaching the exit. More specifically, what we're doing here is we want to ensure that the agent eventually arrives at some target states with probability 1. Okay, important here is that the safety and the reward objective may not be aligned. That means that picking safe actions may be actually decremental for the performance, right? And so that also means that I'm not modeling or assuming anything about what the reward function here really is, right? The safety objective or this productivity is really independent of any reward. But I want to reason a little bit about the safety and productivity of these actions. And so we're gonna reason in an abstraction of this true POMDP underlying the system. So for this part, I will assume that there is a true POMDP, and I will assume that we have an abstraction of that POMDP available to us. And I think this is not a super reasonable assumption, but it's the assumption that we're going with here. So here's the example. You have an agent. The agent has some area in which they can see an obstacle. That obstacle is going to move around. but stay inside this boundary. And what we want to do is we want to only allow actions such that the agent will eventually be able to reach this goal. So yeah, this is how this is going to work. And here there's the actions, and sometimes we're saying like particular actions are not safe. Here at this point, for example, we say, okay, you can go up or you can go right. Both are safe and productive in the sense that from either here or here, there is a path forward where you reach this goal, but you cannot go down, and you cannot go left. And in order to do this reasoning, what we need to do is need to say, okay, it could be true that this obstacle is in any of these pink states, right? Actually, it is here, but that's not something we know. We just know it's in one of these highlighted states. So yeah, and then eventually here the agent doesn't do anything optimal, right? So here you can see it's really not the optimal thing in order to achieve the goal, but that's not what the shield is trying to achieve, right? We're just trying to achieve that it has the opportunity to eventually reach this. So what's the setup here? This is the standard shielding thing that Bettina will say much more about. The setup is that rather than just providing the observation to the agent, we're saying this is the observation and these are all the actions that could be taken in this state. We put it into something that's called a shield, and what we get out of that is the observation and these actions that we call safe. And in order to do so, the shield needs to know the transition relation. And in this particular setting, it needs to know the topology of the transition relation. So just the support, right? Is there a transition between these two states? It also needs some memory. So it's going to track the support of the belief. What are the states that the obstacle could be in? And it needs some offline pre-computations where you need to solve almost sure reachability in POMDPs, which is based on work that we did with Sanjit while I was here. And this works. So shielding guarantees safety. Caveat, if the abstraction includes the true system behavior. Right? And then this works. It is not, in no sense is a shielded agent going to be optimal, but at least it's safe if this property holds. So then we thought, okay, can we also combine this with RL? And this is just an empirical study, so there's nothing deep here. We just thought, okay, if we now take these TensorFlow agents without anything deep, and we are just changing our setup to the following. We have this shield. We are tracking the belief support based on this model, and we're providing the safe actions. So what happens then is that indeed these agents very quickly learn to do something useful. So this agent needs to avoid these obstacles, and it very easily learns how to navigate this. And notice that these are sparse reward settings, right? So we only get a positive reward once we're in the goal. And so this is really hard to learn for an agent without shielding. And here, what we need to do is we need to get to this position, but we have a limited amount of energy on board. And so the only way to get there is to first get to one of these recharge stations. And then from there, you can actually get there. And so here it's constantly trying to make sure that it reaches that. And at some point it manages, and then it knows, okay, from now on, I can easily reach the goal. So this is with a shield, and you can learn this, and this works very nicely. And you really need these shields in order to make this feasible. So I don't want to go into the details of this graph. So this is not a talk about shielding, but really these shields are essential to get this performance even. So this is no longer about safety, right? This is just about symbolic reasoning, allowing you to have a reinforcement learning agent do what you want to do.
Yeah, so this is an interesting angle, right? Because you're saying that your empirical results indicate that it accelerates learning
Yes.
by essentially by restricting the exploration space.
Yes.
But have you seen this across different different benchmarks, so
Yeah.
different environments?
So these are 6 different environments. They're all sparse reward environments, so that's definitely
okay.
So solid lines are shielded, dashed lines are unshielded. Sometimes you really need the shield to actually learn something. Sometimes you can also get away with a little bit more time. There's a lot of data,
okay.
right? So I think the claims are justifiable. There are lots of, it's an empirical study, but we did this with lots of different agents, lots of different.
Right, thank you.
One thing is, I'm just thinking of practical applications of RL in robotics or game playing and all that. I am still unclear who would write that shield.
Like you don't need to provide the shield, right? You write the POMDP. You need to specify this is the POMDP.
Okay, but I'm looking at an end-to-end thing. So suppose I'm using RL style in sort of I don't know, Go or thing. So where is that shield coming from?
So if I start with Go, so Go is not stochastic in that sense. I don't know whether it's a perfect example, but
maybe that's a bad example.
But the rules for Go, right, Go is a nice example in that sense. The rules for Go are clear. So for Go, I could probably come up with an abstract POMDP that describes Go perfectly.
Just the rules of the game, basically.
Yes, exactly, right? Now, of course, there's a huge scalability problem because if you give me that POMDP, I'm not going to compute a shield out of that.
Yeah, I'm just trying to connect it that like if in real examples where they use RL, where will that shield come from?
Let's Bettina answer that on Thursday. I don't want to go into the shielding discussion. But I agree. I'm not claiming that this is connected to any real world applications. I don't want to make that claim. I just want to say, look, RL, these are nice. I think that all of these examples are motivated by some high-level navigation tasks, right? The drone needs to fly from A to B, but it only can do so by visiting some recharge station on its way. I think that's a reasonable assumption, but I don't want to overclaim anything.
Can I give example from a real, let's say, real world example for Shield? So what we did in the class, so I don't know how teaching in the class is a real world, was the following. Students first used LLM to take a legal text and translate it into first order logic. So we used then this translation for a different project where they actually needed to train their own LLMs to do some sorts of classification. And then we're actually, whenever we ask LLM to generate some sorts of new proposed scenarios, and then they would use these shields that were generated in the previous task as, protection. So in some sense, that is how we used, but that's kind of whether it's really real world. But, like I can see that if you will be able to use this maybe to derive spec in one scenario, and then you can use this spec for shielding when you train your LLM. But I mean, that's a classroom example.
Shielding has lots of cool examples, right? Don't get me, but I don't want to go into this discussion because I want to tell you something different than that, really. So why does this actually accelerate things? There's two aspects to this. So the first aspect is that we are actually, by providing this model, we're basically able to provide the RL agent a better estimate of where we are. This is a signal that the RL agent typically doesn't have. It would need to reason about that, and we're explicitly telling it in this, or at least the shield has this information, right? And so state estimation on its own will already accelerate learning. And if you wonder why, so here's a thing where you need to know at the end of some long story whether initially you saw an orange or a blue light. Well, and if you initially saw an orange light, you take one action, and otherwise you need to take the other one. This is hard for an RL agent to learn because it needs to learn that it needs to remember something from the very first step to execute much later. But if you have the state estimate, then this completely trivializes the problem. And then, as Sanjit already rightfully pointed out, the reason why the shield then additionally accelerates the learning is by putting focus. It will say, well, there's no point in exploring particular parts of your state space. And so it's much quicker to start seeing the sparse reward. And then it can start learning much quicker. And really, both aspects contribute to this. So the data really shows that just the state estimation helps, but the effect that we're seeing is the shielding and the state estimates that help here.
So the thing is, are there negative? So there are all these, I did this long time back, all these convergence result for policy convergence for POM-DPs and all that. Is it possible that in some cases with shields, you lose some of these very interesting convergence guarantees and all that? Because you're restricting.
If the reward is aligned with the objective that the shield is doing, then you're not losing it because but it might be that these two, that the performance in signal and the safety thing are not aligned. And then of course you lose it. So, but there's an additional point here which connects to this, right? The guarantee that we're providing here is that eventually a target is reached. And that, of course, is something completely different than saying that we are reaching a target within episode length. And you can see this as well in our experiments. If we're looking at very short episodes, then we're getting really bad performance. And actually, it's better to take the unshielded agent because it will take some high-risk actions. Whereas in the shielded, if these horizons become long enough, then taking the shielded action is better. And then there's the final point that I want to make regarding this is that you can do this to bootstrap your system. So say the shield is now also excluding actions that are interesting. You can still use the shield. And then at some point after 1,000 episodes, say, OK, I'm going to switch the shield off. And if you do that at this point hard, then your performance will degrade, but it's still better than the unshielded version. And if you do a smooth switching off, right? So there's different ways on how you can disable your shield, but you can say in every second step, in every third step, and then actually the RL agent has some time to learn what the shield was previously doing for it. And so you can use your shields to bootstrap your learner to say, OK, and now at least you start doing something useful. And once you're doing something useful, we'll get you additional degrees of freedom. But now you're seeing this interesting reward signal. So I think shields, beyond the safety guarantee, can really help in an RL agent in a way of that we're integrating learning and symbolic reasoning here. Now, the big caveat, of course, was that we need to know the transition relation. And this is typically the thing that, OK, if you're playing games, you know these things. I also think that there are lots of high-level planning scenarios where it's absolutely reasonable to say that you need to know something about the transition relation. And in particular, we're not saying you need to know the probabilities, right? All of this is without regard to of the probability. So we only need to know the topology, and it's not completely unreasonable. But of course, like any other model-based approach, there's this question, what if you start perturbing the model? And is this able to generalize beyond the model? And there's the scalability question. And as always, compositionality is kind of the holy grail. And so I want to talk about these two things here. And then for this particular application, this shield is super conservative. If it's not possible to reach the target with probability 1, then your shield will just say, well, you're lost here. You cannot do anything. So it's nice if you can allow also shields that are more quantitative, but that's computationally even harder. I will say something about that at the end. Okay. So just a little bit of notation. I think we're all on the same page here, but we have an MDP, which has states, an initial state. We have a finite set of actions. Notice that everything in my talks is finite. There's a transition relation. For every state and action, we tell you what the distribution over the next states is. And then if you want, there are rewards, discount factors, and everything, but they're not essential to what I'm telling you. A policy in general maps histories or paths to distributions over actions. And if you have an MDP and a policy, then you can say this induces some value, which can be the expected reward or the probability to satisfy some specification. And there's a Markov chain, which is basically the MDP that takes exactly that action that the policy specifies for that history. Okay. Here's the observation. Policies are not robust against perturbation of the topology. I want to go from here to here. There's an obstacle here, and I can sense that there's an obstacle here if I'm in this state. What is a good policy or the optimal one? You just go right here. You don't need to even talk about the obstacle. Now, if I move that obstacle, if that obstacle would be in this location, then this is a horrible policy. So this is the problem. And this is something that is outside of this realm of can we perturb the probabilities a little bit, right? This is really, you need to talk about a completely different MDP. This can be formalized as follows. There's a set of environments, and this is just a set. And then we can define a multi-environment MDP, which for every environment gives a different transition relation, right? And there's nothing that relates these two things other than that they are over the same states and actions. So for every environment, a different transition relation. And you can think of this as generating a set of MDPs. If you plug in an environment, then you get one specific transition relation. So some of you might think, this looks like a partially observable problem because I'm in an MDP and I cannot just observe in which environment I am. Right, so you could compare this with a POMDP where an agent is in a state where S is the state and E is the environment that it is in, and it only observes the current state. But this is different because here we're really assuming that there is no prior over the environments, which means you cannot trade doing well in one environment for doing bad in other environments. The version with priors is also interesting, but I think this particular version without the prior really makes sense because it really captures this idea that doing bad in one environment cannot be compensated for. It's also easier than the general POMDP setting in a computational complexity sense. There is something that's called the monotonic information gain, so you never lose information. And so various problems that are undecidable on POMDPs are decidable for multi-environment MDPs, including a paper by Krish Chatterjee that appeared last week. So there's still open questions, but this is a tough paper to read, so I cannot tell you everything about that. Okay. Before I continue with the more practical algorithms, you should think of these environments as having some structure, right? So, for example, if I have an obstacle at either of these 12 locations, then I should really think of this as there's an obstacle at a location OX, OY, where OX has some value and OY has some value, right? And the idea will be that environments that agree on most features also agree on the transition relation in most states and actions. Right? So if my obstacle is here, then on most here or here, it doesn't really matter for the transition relation in most of this system. Yes.
Just want to understand the terminology here. So what does feature refer to?
Feature would here be this OX and this OY. So I give you a set of variables.
Is that how it is? The environment is defined in, or is it some higher level feature that extracts structure from the environment? So for example, the environment could be a 2D grid with X and Y, but the shape of the obstacle might be, some kind of special structure, but you could parameterize differently. So are those the features, or are the features just the variables of your
So no, these are not the variables of my state, right?
I think, correct me if I'm wrong, you are modeling different obstacles where that stone or whatever that thing was as different environments.
Yes.
What I would think in like in a robotics domain, won't you have like a sensing action that also tries to sense where the obstacle might, it is part of the spec of the POM-DP or something like that, right?
Yes. So
why would it, is the right thing to model it as a parameterized environment rather than having an action, sensing action or something like that? I don't know whether I'm making any sense.
Yeah, no, of course you could look at this larger system. This is basically the POM-DP that I was referring to in the last slide, where I could say, look, you model all of this as a huge POM-DP in which you have the ability to sense, but then you're throwing away, like computationally, you're throwing away a lot of things because you're now making the problem just much bigger and you're throwing away some of the structure. So I agree, you could model those things. You also have to be careful about the prior, because I think this is, but you could do that. Yes, absolutely. But I think this is a reasonable way of capturing some of this inherent structure that you have. And it resembles, for example, I mean, this is really inspired by things that Sanjit does with the scenic, right? So I think you have a grid, and then there is a variable which says, or two variables which say, which describe the environment by saying in which position of this grid is my obstacle. So these features you should really think about not as properties of the state space, but as properties of the MDP itself. Right. So for if I set this thing, then in my probabilistic program that describes my MDP, these are the same kind of features that you think of in scenic, right? As features, sure. I think.
Right. And then I'm trying, sorry, in terms of notation, just explain P sub E and P sub E prime. They're just the transition probabilities for the environment?
Yes, in two different environments, the transition to the distribution over the next states, and when I'm in state S and taking action A. Right, so I take the same state.
I'm just trying to understand the statement. You're saying if the current state of two environments, E and E prime, agrees on most features, then the next state distribution is...
No, these two environments are close. These two environments are close. These two environments are not so close. That's what I did.
Maybe the term environment is a little overloaded here. So what do you mean by environment again here? Because for me, the environment is the entire layout in which the robot is navigating.
Yeah,
right?
so
the state of the world. Is that
it,
what you mean by environment? Or is something
yes,
more
and here it's uniquely identified by the location of the obstacle,
right?
Because everything else is.
But then, if it's a dynamic environment, it has the environment state can change, right? And two different environments, even if they start in the same arrangement of x's, the next state could be drastically different depending on the dynamics.
Yes.
So I'm trying. So then what does it mean for the distributions to coincide?
So these are static obstacles in this setting.
Okay, in the case of static obstacles, yeah, sure.
So I mean, there's an X, they agree maybe on the X
just
feature.
saying, just a comment about static environments.
Yes.
Okay.
I can do the same thing for dynamic environments, but I want to, this is also, maybe this is not a good intuitive statement.
Yeah, I guess a clarifying question I think to make sure I understand. So this is effectively a trick of reparameterization where I've moved some of the information from the state that you maybe would think that should be in the state, and I've pulled it into the environment model because from a factorization standpoint, that it gives me some additional structure. Yeah, this is mostly a computational trick.
Yeah, I can always create one big MDP that does the same thing. Yeah. One big game actually, but so this is not an answer to the robustness question, but I think it's good to first think about this a little bit. So if I now give you such a multi-environment MDP and some threshold, I want to find a policy for every environment. This is really not formulated nicely. For every environment, I want to find a policy such that its value in this MDP is above lambda. So what would that be? For example, that would be, look, if the obstacle is somewhere here, then your policy should be to navigate like this. If your obstacle is either here or here, your policy should be to move like that. And maybe if your obstacle is here, then there is just no safe policy. This is not robust in the sense that this is really depending on the environment. So this needs your agent to know in which environment it actually is. But it's still nice, and you can try to compute this, right? If you have lots of MDPs, it's still good to get this information, and you can say, okay, maybe I can explain this to someone, right? If your obstacle is far, behave like this. If your obstacle is further to the left, should behave like that. How do we compute this? Very briefly, you take some set of environments, and you guess a policy, and then you try to prove that this policy is robust in the sense that this policy satisfies the specification on every environment. We'll talk about one of these techniques to guessing this policy later, and I will now first say, I will say something about this in a minute. If yes, then you're done. Basically, you can say, okay, this policy that I found is part of my solution, and otherwise you will split, right? Like here, you will split, and then you will recursively create this tree. So there's a fairly simple divide and conquer kind of approach. How do you prove that a policy is robust? This is basically the same algorithm now. You take a set of these Markov chains. So for every MDP, you fix this policy. It gives you a set of Markov chains. Construct an abstraction of this Markov chain because you don't want to enumerate over all of them. Your abstraction is sufficiently strong, you're done, and otherwise you will split the set of Markov chains and try to prove on them individually. In the end, if your abstraction is really bad, then this is just enumerating, but practically speaking, this is not going to enumerate. So this abstraction is really simple. So here are 4 MDPs, and or 4 Markov chains, and they're different in these 2 dimensions, right? So here there's transitions that either go here or there, and there's a transition that either goes here or there. This abstraction is an existential abstraction. So what we're going to do is we're just going to forget in which environment we are, and then we're going to replace. Well, this is going to be a non-deterministic choice, an action choice. So this is going to be an MDP now, where you can, in every state, the environment can now determine along which environment it is playing. Like, are you behaving as if you're in environment 1, or are you behaving as if you're in environment 2? Importantly, every Markov chain in this set can be obtained by picking a deterministic memoryless policy that then creates this Markov chain. And it's a proper abstraction because there are also policies that behave like different environments in different states, right? So this is not possible in either of those 4 environments, but there's a policy that does so. This is a proper existential abstraction. The good thing is, if we're reasoning over all policies, then we're basically just reasoning over an MDP, and this is super tractable. If you think you can solve MDPs, then you can solve these abstractions. And so rather than now enumerating, you're gonna argue over MDPs. Now, this, of course, was not the complete solution to robustness. So what do we do if we want to be robust? We really want to say something about the sensing, right? So even if I'm going to find one policy that is good for this, I really would like it to be to generalize. And here's a solution where I would claim that it somehow generalizes even beyond these 3 environments. Because the solution that we just saw would have been, if you're in this environment, act like this. If you're in another environment, act like that, or act like that. But we can also try to learn such a policy. So what does this policy do? It says, you start here, and If you sense that there's no stone to the right, you will move to the right and go to the target. If you sense that there's a stone to the right of you, then you go up. And then once you're no longer sensing that there's a stone to the right of you, you go here, and then you will go to the right. So as long as there's just one obstacle somewhere, you can even grow this grid, but it will still be a useful policy. So I would claim that if you learn this policy from this memDP, then you somehow learn to generalize. And how do we do this? This has been like notification for acceptance came in this morning. We do policy iteration, and this kind of an image will look very familiar. So we start with some policy, then we do robust policy evaluation with the technique I just explained to you. And either we can prove that this policy is robust, or we will find a challenging environment that is a counterexample to being robust, right? And then we'll perform a subgradient descent step on exactly this challenging environment. This is countering traditional AI wisdom, which would say that domain randomization is a good idea. But our experiments show that it is really much better to do this counterexample driven than with domain randomization. So domain randomization would say you just take random counterexamples. And so we've done some learning and some ablation studies, and these are just 3 examples where you can really see that taking random environments is not gonna help.
What's the y-axis?
So this is the performance, the robust performance, so the value of the worst environment. So you take the minimum over all values, basically, or it depends, or the maximum. So here higher is better. So here you take the minimum and you want to have a minimum which is as high as possible. And in this setting, apparently the cost is split around. But yeah, it's the value in the worst environment that you could be in. It's the guarantee that we can give you. As long as your true model is one of these environments, then this is the performance that you'll get.
In the second case here, domain randomization is doing better, right?
No. So here you want to be as low as possible.
Oh, that's what the arrow
sorry.
means.
Yeah,
okay, you want to be low. Okay.
The reviewers also rightfully complained about that. So we have to fix this. This also generalizes reasonably to unseen environments. So what we could do is we did some stratified sampling of the environments on which we apply this technique. And then we applied the same algorithm, and then we tested it on environments that was previously unseen. And the performance is really rather good, but it's of course much better if you just give it all the environments that you want. But there's some proof that you want to, or some empirical evidence that you want to, that you properly generalizing here. But this all really depends on the ability to do fast and precise, robust policy evaluation with millions of environments. So this is with millions of environments. Really.
So for these experiments, how many iterations of that counterexample guided loop did you need?
That's a great question. I think it's between 20 and 100, and I can give you the exact numbers after the talk.
Let's see. But that compared to the total number, of course, is much smaller.
It's super small, right?
Small,
yeah.
Right? And so I wonder if there is something there where there are environments where domain randomization is actually does better because you need a lot. I mean, this just depends on whether the diversity in the number of environments that the policy has to work for. I mean, so here there's probably some structure that the counterexample guided technique is quickly zeroing on, and that's enough, right? And that also is typical of program synthesis. But on the other hand, especially when you go from discrete to continuous, it's not so clear to me that you'll have that relatively small number of counterexamples that will do everything. But yeah, I mean, I think this is. I wonder if some more targeted experimentation is needed here to evaluate it fully.
Yeah. So this is there's lots of things. So, but on these environments, we see this in particular. What I think gives me some confidence that this is a good way forward is to say that this is actually learning how to generalize, and this is something we're not seeing on the domain randomization. So, by providing these counterexamples, at least what we're doing is really moving this gradient descent on to do steps in the right direction on the places where it's really needed. So in the talk, what I did, I really talked about a fixed policy, but with different MDPs. You can think of the dual setting where you fix the MDP. Now you believe that there is one true MDP. And now you can think of, can I find a good policy here? And this trick really works well for observation-based policies. So if you want to do constraint search in the space of observation-based policies for POMDPs or for decentralized POMDPs, for constrained POMDPs, that works really nicely. Or if you want to search in the policies space that is described by policies that can be interpretable. And they're just, in order to make this point, right, so millions of environments, but here these techniques are searching in spaces that enumeration would not work, and also where I believe that randomly searching in these kind of spaces is not going to work. So this perspective has more to it than just this setting. I'm going to skip over the compositionality in the interest of time, but I would like to say a little bit about the monitoring stuff, if I can. So what is the monitoring problem all about? We're looking at a risk-labeled hidden Markov model here. So what does that mean? We have a Markov chain. Every state has some observation signal. These are these colors. And then there is a risk that describes how much you want to be in the state or not. And here this is something where you're driving either in the dry conditions or on icy conditions, and here you've crashed. This is a very silly example, but I just wanted to have something visual there. Now the key question is, I give you a sequence of observations of dry and icy, and I want to know what's the current state risk in this setting, what's the probability that I've crashed. Right, so this is a conditional probability where you can say it's the probability, it's the sum over all the paths that agree with the observations that I made times the risk of the last state that I am in. Can do this calculation, but I think you will all get this. And this is just state estimation, right? So you can just run your state estimation algorithm. You will find a monitor. So the monitor is a function from this sequence of colors that you've observed to some value. And just for the idea here, right, the perfect monitor is then something that computes exactly this state estimation. So that's fine, and we can do this, and people do this, but now I have a different question for you. I give you the monitor. So this is the monitor, it's a DFA, and it says that there is a high risk if the DFA accepts. My question is this a good monitor? So what do I mean with a good monitor? I'm going to provide to you two thresholds. I'm going to say safe traces are traces where the risk of this trace is below lambda s, and unsafe traces are the traces where this is above lambda u. And then right there are some traces in between, and for those I don't mind. And now a monitor is correct if the language of the monitor contains all the unsafe traces and doesn't contain any of the safe traces. You can think of variations of this problem, but this is what I'm going for here. Sadly, this question is co-NP hard. And also approximative versions of this problem are hard. There is a verification algorithm, and it contains two steps. The first one is that you don't think about this filtering algorithm, but what you can actually do is you can reformulate this problem of what is the risk of a particular trace into reachability probability and then depth of Markov chain. That is algorithmically not a smart idea if you want to do this for one trace, but this is a problem. And now we have here, for every trace, we have a Markov chain. So now verification is just that proving that for every Markov chain, some property holds. And all these Markov chains, right, they're all variations of this original HMM. So the algorithms that I talked about earlier are also applicable to verify monitor correctness. And I think this is really, right, this is a position where, or a situation of a problem where we weren't looking for sets of environments, but still, once you have that hat on, that you're looking for sets of Markov chains, it really comes very natural. Now, this gives you verifying monitors. Now you can also learn them. And for the active automata learning fans in the room, I thought I should include that. So we're doing this with active automata learning. You can do, this is a silly question, but you can do the membership queries via the forward filtering, just as you would do state estimation. And then you can do this equivalence check or an acceptance oracle via the verification algorithm. And this is better than doing conformance checking because there are some, in particular, initially, it's very hard to find counterexamples. The space is huge, and just doing conformance checking will not identify these counterexamples. There's some work to be done, and if you're interested, I'm happy to talk about that as well. And that's it. I'm super happy to also talk about compositionality offline, but I hope that I convinced you that sometimes arguing with models can help, like an RL algorithm, that you don't need to think about the correct model, and that you also shouldn't just think about safety, but that it also just might accelerate learning. There's really useful to start thinking about sets of models, and there are different ways on how you can phrase problems there. And in the end, all the algorithms that we're doing are always some kind of a branch and bound technique that really use that we can do MDP verification very efficiently, right? So that's the hammer there is MDP verification in the end. And we can learn some correct monitors, and there you also want to have this hat on. So that's it. Thanks for your attention.
Thanks, Sebastian. I think we maybe have time for, technically over, but let's say 1 or 2 questions.
Thank you for the great talk. I'm interested in this conformance checking comment, and I can see why in discrete spaces it's very hard. And I think we often think of like in discrete abstraction to actually be simpler, but could it be the other way around, that actually continuous spaces are better for like some of these searches and more efficient, and then we can go back to discrete again? So
yeah, absolutely. I think if you're solving a problem that's on a grid or that is continuous, then discretizing it is throwing away lots of the stability of the, or like the locality of your problem. But there are lots of algorithms or protocols which are inherently discrete, and for those, so I'm most of my work is actually trying to solve problems that are really like completely discrete, and they're not discretized versions of something continuous. But I would be very interested to also think about the continuous setting here, and I agree that maybe it's conformance checking might be good in the continuous case.
And I have one that I've been holding on to. So I like this reparameterization effectively of like pulling in some of the state into the environment set and then doing a worst case analysis over it. And sometimes it looks like you're developing a curriculum by doing that. So if I were to put on my machine learning hat, this looks like a curriculum design kind of problem. And so what I would wonder there is like, is there a natural point in which I ask, can you start off with a full MDP and then try to pull out, these kind of worst case assumptions in order to turn this into a curriculum and kind of accelerate through this counterexample rather than doing this randomization?
Yes, it's a great question. There's a lot in that question. I think the curriculum setting is really this setting where you typically assume that the agent that is learning has access to in which environment it is learning, which is different from the second part. But it could very well be that if you say, I can start learning from these like environments, I pick one environment here, I pick an environment there, that's a good way to construct a curriculum. I'm not sure whether if you do that, you get to whether you solve this problem that you want to, you need to realize at some point that you need to look at the sensing aspect, right? I don't know. I'm not a curriculum learner. So I don't, I haven't tried this, but we thought about whether the resemblance is clear. And if someone in the room knows more about curriculum learning than I do, I would be super happy to talk about that.
Well, if there's no other questions, a round of applause for Sebastian. Thank you. We have a break for 15 minutes. We'll start at.
Just try to restart.